Good morning, students. Today, we are at the next step of our lesson. Remember that in our last lesson, we learned various methods of biasing, and also we concluded that the most popular method of biasing is the emitter is the potential divider biasing. This biasing that we discussed and potential divider biasing, it's also called self biasing, right? And I requested you to subscribe to this channel to help me. Then today we come to the lesson of bias stability, right? While determining the quiescent points, VCQ, VCQ, VCEQ, ICQ, we took into account VBE and beta. You remember that. Also, but we ignored CICBO, which is reverse collector base current. Now, all these parameters, VBE, beta, ICBO, all these parameters, they vary with, all these parameters, they vary with temperature. All these parameters vary with temperature and also age. And new it has some value, but after few years, its value will be different. And that's why you have seen electronics components, its performance deteriorates as it ages. Also, there is one point, these transistor parameters, they are different from one to other. Even if you have the same type number of the BJT, suppose you take BC547, another BC547, you will find their characteristics are different. As a result, what happens? Suppose you are repairing a transistor radio, and you find a transistor is bad, defective. You want to replace it. If you replace it, its characteristics values are different. And obviously, the transistor radio performance will be different. So, this is a problem. Now, we are now going to learn what is bias stability, and then we are going to learn how we can compensate for the instabilities, right? So, this causes instability of the bias and the amplifier's performance. Let us consider the self-biasing technique, which is the most popular technique. We shall do our analysis of bias stability on this circuit, right? It's the most popular circuit. Earlier, we considered IC, collector current, is equal to beta IB, right? Is equal to beta IB. But actual relation is different. Actual relation is, you remember this relation, collector current IC is equal to alpha IE plus IC BO. You learned this relation in your device class in your earlier semesters. And IA is equal to this emitter current is actually equal to base current plus collector current. So IE can be replaced by IB plus IC plus ICBO. So if you take this alpha IC on the left-hand side, it becomes 1 minus alpha into IC is equal to alpha IB plus ICBO. So what is IC? IC is equal to alpha divided by 1 minus alpha IB plus ICBO divided by 1 minus alpha. And we know alpha upon 1 minus alpha is called beta. So IC is equal to beta IB plus this is 1 plus beta ICBO. This is equation 1. This is the actual relation, right? Now, you consider the collector emitter branch, this collector emitter branch, and if you put the Kirchhoff's voltage law equation, this VC is equal to VCC minus ICQ RC, this potential drop, minus IEQRE, this potential drop. Now consider the base emitter loop, this loop. If you consider this loop, then same equation, V voltage here is equal to IBQ RB, because this IBQ is flowing through RB, IBQ RB plus junction voltage VBE plus IEQ RE. Fine. So we get VBB is equal to VBB minus VBE, we take to the left hand side, VBB minus VBE is equal to IBQ RB plus IEQ RE. Now IBQ RB is there. Now IEQ, emitter current, is actually base current plus collector current. So IEQ is replaced by ICQ plus IBQ into RE. So this becomes IBQ into RB plus RE plus ICQ RE. From here we get IBQ RB plus RE. This ICQ we take to the left hand side. IBQ RB plus RE is equal to this VBB minus VBE minus ICQ RE. So what is base current IBQ? Is equal to VBB minus VBE divided by RB plus RE minus ICQ RE divided by RB plus RE. This is another equation. Now we put the value of IBQ from this equation 3 in this equation 1. IB, we put this value here. If we put the value here, what do we get? This was ICQ is equal to beta IB, beta into this whole IB here, plus 1 plus beta ICBO. Then we multiply, this is beta multiplied by this factor, minus ICQ beta RE divided by RB plus RE plus 1 plus beta ICBO. So here is a ICQ factor, we take it to the left hand side. So ICQ into 1 plus beta RE by RB plus RE is equal to, on the right hand side I have beta multiplied by this factor plus 1 plus beta ICBO. From here we get ICQ multiplied by, we make this simplification, is equal to this and this. Okay. Now, this is, so ICQ is equal to, from here we get ICQ is equal to this factor beta VBB minus VBE divided by RB plus RE, and whole thing is multiplied here, and this becomes my equation 4, right? This is a little lengthy equation, but let me tell you, I don't think for your semester examination purpose you need to remember all these equations, but you need to remember the outcome of these equations, what you get finally. And particularly if you are applying for, if you are sitting for competitive examinations after various competitive examinations, this may be necessary. So we have this value of ICQ of equation 4. This equation gives the correct value of ICQ. Earlier we have taken ICQ is equal to beta IBQ, but that was an approximate equation. This is the correct equation. Now you find ICQ, or the quiescent collector current, depends upon VBE, the base emitter junction drop, depends upon beta, also it depends upon ICBO. And all these three parameters are temperature and age dependent. Also, here, next step, this is the exact equation. Now we do a little bit of simplification. This beta is much more than 1 in a transistor. Beta is minimum value you will get 100. Maximum value you get few hundreds. So beta is more. So 1 plus beta can be taken equal to beta. So ICQ is equal to beta VBB minus VBE plus beta RB plus RE into ICBO divided by RB plus beta RE. Or we divide both numerator and denominator by beta, then ICQ becomes VBB minus VBE plus RB plus RE ICBO divided by RB upon beta plus RE. This is equation 5. This is a simplified equation here. And after this simplification, it becomes easier to handle. This equation 5 shows that, see, in this equation, we have beta only here. Fine? Have you noticed it? We have beta only here. So, it is clear that ICQ, ICQ will become independent of beta if RE is much, much more than RB by beta. That is why we have derived this equation. So, the beta or amplification factor of the transistor will not vary from one to other, can satisfy this relation. That is a very crucial outcome, right? You should remember this. Emitter resistance RE should be much more than RB by beta. Now, later on, when we go for transistor design, some students ask me why there is a RE, because this is some AC power loss here. This reason becomes, if you have a RE and maintain this relation, then this biasing becomes beta independent, right? That means, where it means RB should be very small. This means RB should be small or RE should be large. Now, let us decide as an engineer what we can do. Mind, RB should be small or RE should be large. But if RE larger, then there is some output power loss in the RE, because we are taking output power from here. The output power that is consumed here is lost. Large RE causes a signal power loss at the output. And if we take small RB, then signal power, input signal power will flow through this, and there will be signal power loss at the input. So we are actually in a catch-22 situation. If we make RB small, then there is a signal power loss at the input. If we make RE large, then is a signal power loss at the output. But we have to make RB small, RE large. How do we do it? So after a lot of trial and error, engineers have found an empirical relation that RE should be at least 10 times of RB by beta. So RB by beta is equal to RE by 10. Or we write RB equal to beta RE by 10. This relation you must remember and just put this relation with a nail in your brain. Whenever you design a transistor amplifier, maintain that RB is equal to beta RE by 10. You cannot make RB smaller. You cannot make RB bigger. Right? So here we wanted RB by beta to be smaller than RE. Don't make it 100 times smaller. Then you will be in a problem. Right? Make 10 times smaller. This is the empirical relation. RB equal to beta RE by 10. If you do that, then we approximate this. We remove RB by beta from this equation, and ICQ becomes VBB minus VBE by RE plus ICBO RB plus RE by RE. So this is equation 6. Right? So ICQ or quiescent collector current becomes independent of beta. So this was the equation of equation 6. So we have studied the effect of beta in the biasing or quiescent current. Now we study the other effects, right? Let's now study the quiescent current. ICQ changes with how ICQ changes with ICBO, VBE, and beta, right? This equation 6, we are studying the temperature effect. So we divide ICQ by del T, differentiate it by del T. Here, VBB is constant. There is no differentiation. So this is 1 by RE del VBE by del T plus del ICBO del T 1 plus RB. This is equation 7. So you find that temperature differentiation, or you can say the temperature dependence of ICQ, is dependent upon temperature dependent of VBE and also temperature dependence of ICBO. If we can find out these two factors, how they are temperature dependent, then we can also find out how my quiescent current will be temperature dependent. Now, here there are some relations. We did not go into the detail of what are those how those relations have been derived. But remember, del VBE, temperature dependence of VBE, that is junction drop, is minus K1 del T. As temperature increases, the VBE decreases, and K1 is 2 millivolt per degree centigrade. So from here we get del VB del T is equal to minus K1, right? And for ICBO also has been found. ICBO2 is equal to ICBO1 exponential to the power K2 del T. There is the exponential relation, right? This is the earlier or initial ICBO. This is the final ICBO. This is the temperature difference where K2 value is given. So from here we get ICBO2 minus ICBO1. That means difference or increase in the ICBO is ICBO1 exponential to the power K2 del T minus 1. Right? So ICBO, this is the del ICBO. So this del ICBO by del T will be ICBO1 by del T into this factor. Right? Now, so from equation 7, we get del ICQ del T 1 by RE, del VB del T is minus K1. So it is K1 by RE. And this factor 1 plus RB by RE. Then del ICBO del T is this equation. So we put this equation here. So now we multiply both sides with del T. So del ICQ is equal to K1 upon RE del T plus this whole factor, and ICBO1 remains del T vanishes. So this is equation 1, equation 8. It shows if there is a temperature difference of del T, what is del ICQ? This factor multiplied by del T and factor, and there is the exponential relation of del T, right? Equation 8 gives a direct relation between the change in temperature and change in quiescent current. So in our earlier page of this presentation, we learned how ICQ depends upon beta. Now we are finding how ICQ depends upon temperature difference, del T. That is the equation. Now quiescent current changes with these three things. Now, so we have got the final relation here, equation 8. Now, we are not going into further deductions, right? These equations will be necessary to you if you are higher studies after BTech or BE. I've seen changes with ICBO, VBE in beta and beta. Accordingly, three definitions have been defined. Changes with ICBO is called S or SI, that is stability factor. And this question you face in your semester examinations very often. What is stability factor S or SI? Is del ICQ by del ICBO. That means the rate of change of quiescent current with the rate of collector base reverse current. And SV or S dash is the del ICQ del VE, the rate of change of quiescent current with VBE. And third one is S double dash or S beta, which is del ICQ del beta. That means rate of change of quiescent current with beta. Now from equation 6, we find S1, SI or S is del ICQ del ICBO, del ICQ del ICBO. If you do this workout, this is not dependent on ICBO. Del ICQ del ICBO is only 1 plus RB by RE. So SI is 1 plus RB by RE. Mind it, we are once again landing up in a relation of RB and RE. These two are very important resistors in a transistor design. And S dash or SV is del ICQ del VBE. If you do here del ICQ del VBE, this is only 1 by RE, minus 1 by RE, equation 10. And to determine S beta, what is S beta? S beta is del ICQ del beta. Now from this relation, finding out del ICQ del beta is very difficult directly from here by differentiation. So what do we do? From equation 4, what do we do? First, we ignore this ICBO. This is a very, very small current, right? So this approximate of equation 4 becomes ICQ equal to beta VBB minus VB divided by RB plus 1 plus beta RE. It becomes simple. Now consider beta changes from beta 1 to beta 2. Accordingly, ICQ changes from ICQ1 to ICQ2. So using this relation, ICQ1 is equal to beta 1 and beta 1 into this factor. ICQ2 is equal to beta 2, and this factor. Now, if we divide ICQ2 divided by ICQ1, ICQ2 is beta 2 into this factor, and ICQ1 is beta 1 and this factor. So it becomes beta 2 into this is beta 2 into B plus 1 plus beta 1. Now this is a pretty lengthy equation. And once again, I say, don't get nervous. You don't have to really remember these equations, but I am giving you these equations so that you can use it in future in your higher studies when you want. So this becomes, see, beta 2 into RB plus 1 plus beta 1 RE, because this VB minus VBE, this cancelled on both numerator and denominator. So this becomes beta 2 into RB plus this thing, and here it becomes beta 1 multiplied by RB plus this thing. So this is equal to beta 2 into RB plus this. So on the left hand side, what we have done, ICQ2 divided by ICQ1 minus 1. So on the right hand side also we do minus 1. So this numerator remains as it is, and the denominator remains as it is. Numerator becomes beta 2 into this factor minus beta 1 into this factor. So ICQ minus ICQ1 by ICQ1 on the left hand side. On the right hand side, if you simplify this, you will get this relation. Finally, this ICQ2 minus ICQ1 is equal to del ICQ. So del ICQ by del ICQ1, simple simplification, but I have given you all the details, is this relation, right? So del ICQ by del ICQ1 is beta 2 minus beta 1, that is del beta, and RB plus RE, this is beta 1 plus. Now, you see this relation, we have not found out del ICQ del beta. So now from this here, we can find out del ICQ del beta. If del beta we take to the left-hand side denominator, then we shall find out, we shall get the, so what I find, so this is the final relation of your del ICQ and del beta. Of course, I agree the relation is very cumbersome or difficult to remember, but don't remember this. Just keep the note in your notebook. You will need it primarily when you go for detailed design or if you somehow get a job in analog system design. Finally, what we have to remember is del ICQ is SI del ICBO, because, let us go back here, there are three stability factors. This is one delta, one differentiation, that is another, this is another. So if all of them keeps on changing, if ICBO changes, BB changes, del beta also changes, then of course the total change is the sum of all them. So if this factor SI is given to you and ICBO change is given to you, you can find out what is the change because of this. SV is given to you. If del VB also given to you, this creates some change. Similarly, this, the third part of all these three components of changes makes the final change of del ICQ. So this is what I have to tell you about what is bias stability. Because often in your Viva question or job interview question also you face this question, what is bias stability and why it is so important to know. So we have learned why it is so important to know. We have learned what are the various components of bias stability. And in our next lesson, we shall learn bias compensation. How this instability can be removed or at least minimized. That we shall do in our next lesson. How this, what we can do to minimize these instabilities. Okay, that we shall learn in our next lesson.